So I was saying that we are all welcome to another edition of weekly AI machine learning get together. And we are going to be continuing from where we stopped last week, where we look into the applications of machine learning in animal production. That's the title, Application of Machine Learning in Animal Production, revisited with practical demonstration in Weka. That is, it means we add several series on the what are the possible applications of machine learning and AI in animal production, the precision agriculture, that is precision animal management system. So where we discuss several possibilities and will graciously refer us, especially some of our new members, we refer us to check out some of the recorded videos on those series. We earlier also dealt with animal production extensively, with also practical demonstration in Weka. So this is the second day we are looking into practical demonstration related to animal production. So we, under our important clarification series, with the team always let the data speak. Always let the data speak, where we have to make sure we are using the right approach, we are doing things right, so that we will not be missing important insight from the data. Because every data set is coming with its own information hidden inside it. The human being we can't decipher it. So we need system algorithm like machine learning to be able to get in there and then be able to unearth or reveal the hidden insight that can benefit humanity a lot within those data sets. So if we use the wrong algorithm, we may be missing out on those insights. That's why we have to let the data speak, using the principle of letting the data speak, which we have codenamed. You start with very simple algorithm, and then you keep increasing the complexity of the algorithm, following the basic principles that we've actually itemized. So last week we've discussed over this. We're going to go straight to further practical demonstration this morning. The importance of agriculture cannot be overemphasized. So without agriculture, no matter how technical know-how, how technical advancement, how scientific advancement has gone, human beings, we have to consume. They have to eat. It's a natural phenomenon. So as our population grows, then we have to devise way of even making the production easier and sustainable. To have a sustainable production is very essential. So hence the need to introduce some of these technologies. We also look into the key goals is to improve productivity and efficiency, enhance animal health and welfare, reduce environmental impacts, while also enable sustainable livestock management. That sustainability is a huge word that in days we cannot finish discussing it. So we want to ensure that we have sustainable animal production, after which we also mention some of the possible things we can use, some of the intervention, how we can have automated weight tracking, feed optimization, behavioral monitoring temperature, detect abnormality and stress at the very early stage, and also improve animal comfort and reduce mortality. All these we extensively discuss as some of the benefits or application example that can come from what we call precision livestock farming, which is made up of using AI and machine learning in the system of farming. So we made a case for predictive machine learning solution that with data, provided we have data, the availability of data set, we can actually be able to have predictive solution that might actually support us in knowing ahead of time some of the proactive measures that we may need to do or we may need to take to be able to prevent trouble and ensure sustainable animal production. As usual, we also refer us to this general framework, the iterative process, towards letting the data speak, where you have the data zone, where you have the data preparation, pre-processing, feature engineering, all these form under data. Then we have the algorithm. In order to let the data speak, I told us we have to make sure we start from simple algorithm. Don't jump to complicated algorithm because it is in vogue. No, we don't do that. You may miss the insight that is hidden within that data set. So start from simple algorithm, and then progressively we move towards the more complex ones. Because the fact that somebody used an algorithm and it got the result excellently well does not mean that in your new data set you are going to get the same thing. Machine learning modeling doesn't work that way. And the earlier we realize that, the better. So that was why we also brought up the what we refer to as more the modified iterative machine learning modeling framework to support the principle of let the data speak. So once you have your data, you bring it in. You don't need to bother much with, once the data can run, bring it in. So don't do too much pre-processing, because too much pre-processing may actually lead to what we call data mutilation. See, data mutilation. When you mutilate your data, in the course of that, you are actually removing some of the important features that will be able to let us understand the secret behind this data set, the hidden treasure within the data set, because this is the new idea. That data set, even though they are thrown away in most places, they actually had huge treasure hidden within them. And that's why it is stated that the next oil and gas is data. If you can make good use of it in your company, in the society, then it can facilitate a lot of things, especially the idea of sustainable development, which is one of the very unique UN goal and aspiration. And that we have seen it working in real life if we're able to take proactive decision making, preemptive solution based on AI and machine learning, we can go a long way to ensure sustainable development. So last week we brought in a data set I'm going to show us now. The moment you have your data set in, the first step is for you to run the experiment, which we did last week. Run it quickly, see what you can get. Is it okay? Is it not okay? This is the first point of call. These are options. Try to do the hyperparameter optimization. Do the hyperparameter optimization. Change the hyperparameters. Is it working for me? Are we getting something reasonable? So we did this yesterday, if you remember. This was the run we were making. Yeah, this was the data set. We brought in this data set. The actual data set was this. See, it has dates, it has number of hens, and there are eggs per hen per day, mortality rate, feed cost, then total eggs produced. And then you have the revenue. So we decided to say, okay, we want to investigate. Can we predict the number of eggs that we produce, provided with all these earlier parameters? That was why we went into, that was why I'm currently displaying the Excel file, and I do hope we can relate with that. We can see my Excel file. Yeah. So those are the features. We call these features. These are the features, the inputs to the system, where this one is the output. So we decided to say, okay, we want to remove revenue, because if you know the number of eggs, revenue will always vary. It depends on the price of eggs outside. That will determine the price, the revenue. So in that case, once we know the number of eggs produced, we can do this. Sometimes also we may want to predict the revenue we are going to generate. That's also fine. That means your target include number of eggs, and then your revenue is this. So sometimes we might even build a kind of a forecasting scheme, time series, using previous revenues to also predict the next revenue we are expecting from our farm. It's also a possibility. You see? Okay. Thank you. So now we're going to the Weka environment and see what we did last time. Yeah, so last time you remember, we were able to run some experiments. So we go to classify. This is the process where you have your data set. So we actually remove a couple of attributes. If you remember, we just undo. So we have date. We said date. We don't need the date. We decide to remove it. So that was what we did. When you select, is remove. Number of hen is okay. Eggs per hen per day. Yes. Mortality rate, feed cost, total egg produced. We also say, okay, for now, we are not dealing with revenue. We decide to remove revenue. Select it, remove it. Yeah, this was what. Then we were left with total eggs produced. We want to predict the number of eggs that we produce, provided we have this information in. And I think at that point in time, we were able to achieve performance measure of up to like 57.8%. I believe Lindsay classifier, we did some, yeah, we started with K-nearest neighbor, which is one of the very simple classifier. And it was giving us this. Then we did what we call hyperparameter optimization, which is the first point of call that I mentioned to us. Once you have you select your algorithm, you do the hyperparameter. You click this, K by default is equal to 1. I also show us another hyperparameter that is very important is the one we call the distance function. Presently, it is Euclidean distance. We have other options, Manhattan distance, Minkowski distance, Chebyshev distance. So you have to check one by one which one is going to work for you. Euclidean function may work for your data last week. The new data you're having, it may not work. So this is called hyperparameter optimization. You can do a very simple one. For people starting, I usually recommend using a very simple mode of doing it, which is, I call it systematic hyperparameter optimization, and make it easy for you to understand what you are doing. Later, you can go to automation. Automated one will do everything for you. You may not even understand the way it did it, but you just get the result. It will recommend the best for you. Yeah. But at the beginning, we selected the K is 1. You start with K. You keep this one constant to Euclidean distance. All the others are ordinary parameters. All of them are parameter in computing. When you say parameter, these are values that you pass to a function that you want to run. So this is why I call it a function. I want to run that function. It has KNN, batch size. All those are parameters. But there are only two that have direct implication on the algorithm performance. Those one, we call them hyperparameter. So somebody will ask, what's the difference between parameter and hyperparameter? Parameter has all the value that you want to pass to a function you want to run. KNN is a KNN number of K is a parameter. Number of decimal places is also a parameter. See, however, the distance measure is also a parameter. However, number of decimal places has nothing to do with the performance of the algorithm. It's just telling us how the result should be shown to us. Should it be in 3 decimal places or 4 decimal places or 2? The default is 2 decimal places. This is enough for us. That is ordinary parameter. However, for number of K, number of neighbors to be used, this is hyperparameter. Because you will notice as we change the hyperparameter value, you see the performance will keep changing. You see the first one, which was 1, we achieve 57.8 correlation coefficient. When we made it to become 2, it changed to 71%. If you follow what we did last week, 74. As we are changing, 78. As you keep changing 78.35, it was increasing, it kept increasing until it starts going down again. See, at a point it starts going down, then we also check the hyperparameter. So you keep checking here. Yeah. I think the best was like 5 for us. Then we go in here to change the Euclidean distance to Manhattan distance, and then you can run it and then see what result you are getting. Start. You can see. So we keep changing in and play. This is the first point of call that you try to say, okay, can I improve the result? After you have done the hyperparameter optimization, you keep noting down the result. Usually, we recommend for you to have a kind of a small plot whereby where you can check what you are doing. See, as you are running and changing the hyperparameter, this is case 1, case 2, case 3, case 4. Excel can generate for you easily. You see, the performance was going up, going up, going up until it start coming down. So we now pick it. The best value is k is equal to maybe 7, for example. So you are going to keep that one constant, 7 for k, and then you start changing the distance measure. Shape measure, Manhattan, Euclidean. You also have another plot that will indicate how it goes up and then comes down. Then the one that gave you the best, sometimes you may have the best at the beginning. The case, the first maybe Euclidean distance gave you this value. As you keep checking it, it was going down until it got to very bad result. So this, it means this guy is the best. Even in number of k also, we have had the case whereby the best number of k was 1. It means you have a plot like this. Whatever plot you have, it doesn't matter. What matters is you are able to identify which hyperparameter value works for your data set. And there is no unique hyperparameter value for all data set. It doesn't work that way. Let us take that. And that is what we call let the data speak. For one data set, the best value of k will be 1. You'll be surprised. If you try to 1, 2, others 3, 5, 7, 8, 10, 11, 12, you keep getting bad result. So you have to go back and choose 1, which is the default hyperparameter. You see, this is how you do hyperparameter optimization. Once you are done with the hyperparameter optimization, the best we could achieve in this example was the case was the, I think, yeah, the best we could achieve then was like, I think that was 57, 70 or 78, 78.25. That was the best. At that point, we thought that perhaps this is the best k-nearest neighbor can give us. Once you have exhausted the hyperparameter optimization options, then it is time for you to change. Try other algorithm. You change to support vector machine. We tried support vector machine. If you remember, we were getting 77. And I said, okay, you have to 78. It became 78. So in that case, you need to go back here. Support vector machine is under function. SMOREG, that is SMOREG. So you see the default hyperparameter is C is 1. The most important one is the kernel. So by default, you run the experiment using percentage split of 70 against 30. So we have our result. It's 77. And already also I displayed to us last week how you can check the actual prediction. In your own system, you may not have the actual prediction display for you to see. You have to go into more option here. When you click more option, you go here, you see, choose how you want the result to be displayed, plain text. Default is usually null. If I choose null and I run the experiment now, it will run, but I will not get any result. This is the only thing I'm going to get. I'll just get the result here, the final performance measures. The actual prediction will not be shown to us because I requested it to be null. So you go here, it's always good to see your result. Show me plain text. You can decide to send it to CSV file or whatever way you want it. Let's with plain text. It means it's going to be displaying it for us. So I run it. You can see it is back. We are getting 77%. Root mean square error is going down a little. Here you can visualize. You can even take this and take it to Excel and plot it for you. You can also have a way of plotting it even in also Weka. You can see here, this is the actual value, this is the predicted value. This is the error. See, the smaller the error, the better. I think I found one here with very small error. You can see here, 2226, prediction is 225 point. That is very, very, if you plot this against this, you'll be seeing that this one is almost sitting on top of it. The closer the predicted value to the actual, the better your model is. That is why sometimes we just look at it, 77 out of 100 is still far away, or it's 0.77 out of 1 is still far away. But then you may not really appreciate what you are doing. But when you plot this against this one against this one, then it makes you to really appreciate what you have been able to achieve. So then you go into hyperparameter optimization. We choose the RBF and see what we are getting. 78. It seems to increase a little bit. Okay, we might now go to C, regularization factor C. Let's make it 100. You keep increasing the value. Let's see, maybe we are going to get something better. 78. So I'm making it to 1,000. Sorry. This one out, it's 1,000. $77 also. So you keep changing this and changing that, then say, okay, which one is actually contributing? So we are not able to make more improvement. So maybe support vector machine is not able to model the data. Of course, depending on the problem. In some areas, 77% is a very good one. 231 root mean square error. So you have other algorithm there. You can go to 3, like MP3, and then run the experiment. 78. This is the range that it seems the data set is somehow. Then it is now time to start checking. What can I do next? There are still other algorithm you can actually try out. There are still other algorithm. So maybe neural network. Why not see neural network? Go to function, multi-layer perceptron. Choose multi-layer perceptron. You run the experiment. 77.99. So it means the data set is somehow that no one is going beyond that one. Then at that point, maybe it is time for us to do what I call attribute selection, because the number of features is a little bit more, 1, 2, 3, 4. However, the number of samples is limited to 500 samples. So in that case, maybe if we do attribute selection, we may get better result. Who knows? So we can do attribute selection. So in doing attribute selection, we can use ranker. Yeah, we can use ranker. So which is going to rank the attributes for us. Okay, we can use correlation. Let me say correlation of the attribute. I want to find the correlation between the input and the output and see which one may work for us. So you calculate the correlation. You can see here, we just use the ranker and the correlation with attribute selection. So you have, these are the ranking of the attribute. X per N per day, number of Ns, feed cost, mortality. You can see 0.59 X per N per day has a very high average correlation, 0.59. The higher, the better. When you talk of the higher, it's absolute value, not either negative. If I have a negative, let's say I have a negative correlation of 0.9. Negative correlation of 0.9 is greater than positive 0.59. It only means negative. As one is increasing, the other is decreasing. They are moving in opposite direction, but they are doing that at the same rate. So you can have negative correlation and you can have positive correlation. So the absolute value of that correlation is what you are going to take. Because I do see people make this mistake. Whenever they get positive correlation of 0.59 and another negative correlation of 0.76, they assume that 0.59, because it's positive, is better than negative 0.69. That is not correct. So indeed, what I'm saying is this, make it clearer. You calculate the correlation coefficient between input and output. One is having 0.59. Another one is having negative 0.67. So when you want to see which of them is better in correlation with the output, this guy is the better one. See, we are going to take the absolute value, absolute. So 0.67 is greater than this. But the meaning of negative correlation is that this is between input A and the output Y1. It means, negative means as A is going up, Y1 is going down, but at the similar rate. Whereas for the other one, for this one, as A is going up, this one also is going up. They're in the same direction. So negative correlation only indicate that there is a kind of a correlation between the way the two variables are changing. One may be on the opposite side, while if they're on the same side, it will be positive. So that is why we cannot judge that 0.59 is greater than negative 0.67 when we talk of correlation coefficient as a means of selecting a variable. Now, let's go back to our variable selection now. Now we can see here that it ranks X per N per day, number of N's, these are high ranking. Feed cost, negative 0.0, very low. So it means if maybe I can remove this feed cost, and this one, they seem to be contributing very little. Let's try that. Feed cost and mortality rate, let's remove those attributes, and then we'll be left with two attributes that achieve a little bit, not too high. We are looking for something with 100% correlation, but there's nothing closer. And the moment you get 100% correlation, then there's a problem. It means that attribute cannot be used for that prediction. It means that attribute is almost the same thing as the target. So we will remove it from your prediction. This is another thing we use this kind of thing to decide. Once you have an attribute that is having almost 100% correlation with the predictor, it means they are almost the same thing. You need to remove that from your attributes, except you are sure that they are not the same thing. But something will be wrong. But 0.8, 0.9, that's okay. That's still fine. But the moment you have 100%, the only variable that can have 100% with another variable is if they are the same thing. Like somebody give you date of birth and birthday. I mean, sorry, the number of years. Somebody gave you have a variable that is date of birth and another variable that's number of years. If you find the correlation between the two of them, you see the correlation will be very, very high. It will most likely 1, because date of birth is the same thing as the number of years you have spent. So in this case, we say they are highly correlated because they are the same thing. We are just calling them by different name. So whenever you have a correlation that is 100% with the target, you have to be careful. You may be using a wrong feature in your analysis. Now that we have identified that feed cost has very low correlation, we can remove the two, because the more the number of features, the more the number of samples we need. With these 4 features, ordinarily we are supposed to have 10 raised to power 4 samples. 10 raised to power 4, that is going to be like 10,000 samples, but we're having only 500 samples in this data. It means the number of samples is far, far lower compared to what we are supposed to have to get reasonable result. Maybe this is what is making us not to get what we want. So now we go to classify and then try to see in the process. Let's remove feed cost and mortality rate. We go to remove the 2. Undo. I remove something I'm not supposed to remove. I'm removing feed mortality rate and feed cost. Remove. Yeah. So I'm left with number of N's and X per N per day. Remember, those are the two that had very high correlation. or very medium average correlation, not very high, 0.59. It's not too high, it's like average. This one also says average 0.4. So now we go back now. Once you remove the features, the new algorithm, the new model you want to build will be using only these two to predict this number 3. This is what we have just done now. We have removed others. The new model will be using only 2 to predict the last one. So now here we go. Let's check it and see. This is called feature selection. What we have just done is feature selection. So we go in there. We try to see, okay, let's go back and use our friend. Now, once you do feature selection, it's as if you're having a new data set. And that's why it is better, if you really want the data to speak, it's better to start afresh with even simple algorithms. Try to build new algorithms. We go back to our IBK. Do the hyperparameter optimization again, because now the data set is different from what you started with. How? You have, out of 4 some attributes, you have removed 2. Sometimes they may not make much difference, but in some cases, they may have made serious difference. That is why it's always good to check and double check. And that's why when you have a pipeline technology or system, it's good to have multi-channel pipeline, whereby you can always run several versions of your models. I think just by clicking it to check out what improvement you are getting. So we're still using the same percentage split. Now we have IBK with default parameter 1 for K, number of neighbors, and Euclidean distance also as the measure. So we are going to run it now. Now you can see something here. The result went bad, seriously bad. Can you see it went? We used to get like 60 something. Anyway, we can't comment yet. If you remember, somebody remember the first one we built last week, I think it was this, we were getting 57.8 with all the 4 features. If you see, remember. Now the new one is giving us 60.5 before the hyperparameter optimization. So which means it is better, because this is the default k-nearest neighbor. The result is better than what we got before, because now the feature has been reduced from 4 to 2. Now let's try to do hyperparameter optimization and see. Maybe we'll get something better. Let's use 5 and run the experiment. You can see it has moved to 74 with 5. So we build for 9. K is equal to 9. 74. K is equal to 11. 75. It's still increasing now. Okay, maybe 13. This is called hyperparameter search. See, in as much as you keep increasing, you keep changing it. You keep changing it until the result goes down. This is what you have to keep doing. Let me try 21. See, in as much as it kept increasing, you are going to keep changing the number of K. At a point, the result will go down. At that point, it says, no, I can't understand anything again in this data. That means you've reached the maximum possible value for you. And then you can go down to the one that gives you the highest and, or if possible, the smallest value of K. Now, maybe time for me to also play with the distance measure. Try with Manhattan and then run the experiment. Now 76 with Manhattan. So you can see that we're getting a little bit better result. Then you have to again go back to other algorithm you have actually used, like the function. Neural network is there. We're also getting 77. Mind you, neural network also you have to do the hyperparameter optimization as it goes. So we also look at SMOREG with having 2 features. So we change it from polynomial, basic RBF, thinking maybe we're going to get something better. 78 is getting closer to 80. See? Okay, maybe we need to increase C to 100. Some 7. See, 0.1, it can take any value above 0. You can see. With 0.1, you can see that it's not able to do anything. This is called hyperparameter optimization. You see, it's not able to produce any correlation. So we say, okay, 50. So you keep checking. It seems what worked for us at this point is maybe 1,000. So we keep checking it out until we get the best that work for us. Sometimes, depending on the nature of the data set, so you may not be able to get what you are looking for. After trying several ones, maybe you are the first one to work on this data set. Maybe it is time for you to start writing your report. And then you can write your recommendation. The next time, it seems the data is a little bit tough, it's not highly correlated, that we can come up with ensemble. This is when we go back here and then try to say, okay, what next can we try? I say, you change the algorithm. We have gone back to reduce the feature, data reduction. See, what we have done is attribute selection, feature selection, we have done this. So you have that privilege to always go back to do one or two things that can get your result better than previous one. So one of the things you may have to start looking for later is maybe I need to start building ensemble method, when you're going to match the result of multiple models to form one. They can jointly, you can take the average of like 151 models, train independent models, 151 of them, take them and then find the average. Perhaps it has been shown severally that it often produces better results than individual. But we don't go there because it takes a lot of work until it becomes very necessary. This is in line with the principle that let the data speak. But remember, start simple. Check the simple algorithms out, check the upper parameter optimization, change algorithms, and then start to look backward. Can I do the feature selection? Maybe I need to select maybe some data set there, they are not even good, they're outliers. We have more cleaning may need them, there may be need to do more cleaning. Okay, so we have to keep going back. Sorry, I think I was muted due to the technical glitch. So once you have your data, you find whenever you change anything in your data set, always try to go back, start from simple algorithm, try to change them and do hyperparameter optimization, change the algorithm you are using to another one, start from simple to complex, and sometimes you might have to go back and do feature selection. We just demonstrated that. Sometimes feature selection may increase the performance of your model, and sometimes you may need to do more data cleaning. Maybe some data samples there are not just good. They are the one causing trouble for your modeling. We may have to do more cleaning. But whenever you do that, sometimes we may have to normalize, especially when you're dealing with regression problem or any other problem. You normalize your data. Sometimes it can produce good result. However, never normalize data immediately. See the performance without normalization, compare it with the result after normalization, and see which one is giving you better result. That is the principle of let the data speak. If you just go normalize the data initially without checking the original data, you may be surprised that the original data is having better stuff for you than the normalized data. That is the reality of data. You never can tell. Last week, normalization worked for me. This week, it may not work. And that is why we have to check various possibilities and then try it on board and then see how far you can get your result better. I really want to believe, because of our time, it is a good place to call it a day. We're going to take a couple of questions and questions if there's need for that, if there's any question, so that we can clarify any gray area that may not be clear. Once again, thank you very much for the patience and for the attendance. Wishing you all the best. Thank you very much.